Assalamu alaikum. Best regards to all the attendees in Nanotech Solutions Canada free international seminar series. Uh, Today's seminar is by Dr. Saifullah Jamali, researcher from Pakistan. He will talk about the elemental characterization of cosmetic use uh, using different spectroscopic techniques. Dr. Saifullah is a researcher. He is his bachelor degree in physics in 2013. He did researches on laser induced breakdown spectroscopy, femtosecond and nanosecond laser ablation of materials, laser ablation in various gaseous liquid environments. He has many skills in computing and analysis, problem solving, research, information management, as well as interpersonal leadership skills. Dr. Saifullah Jamal has published many researches with his colleagues. And let's go on and start our seminar today. You are welcome, Dr. Saifullah, and all our attendees. So let's begin.
Thank you very much, Doctor. Bismillahirrahmanirrahim. I am Saifullah Jamari, researcher from Institute of Physics, University of St. Jamshoro. Today I present my research lecture on nanosecond laser interaction and elemental analysis of cosmetic agent using spectroscopic techniques. So this is the university, the location of university in a globe map worldwide, and this is basically our library, so-called central library. It is the biggest library of our university. Now presentation plan. My today's presentation plan consists of aims and objectives, introduction of LIPS, sample preparation, sample and its preparation, experimental setup, results and discussions, conclusion, and finally references. Aims and objectives. My aims and objectives are to study the nanosecond laser interaction with cosmetic agents, to find out the trace elements in the cosmetic agents, to study the hydrodynamic variations of emission line with a delay time, to study the plasma parameter such as electron temperature, electron number density, inverse beam stalling coefficient, and plasma frequency, and to find out the concentration of trace element present in cosmetic agents. Novelty of my work. Many investigators believe that throughout the globe, cosmetics are responsible for poisoning due to high concentration of heavy elements. An extensive analysis of cosmetic users and non-users found that those who use cosmetic daily are often in skin disease like skin rashes, multiple stretch marks, yellowish brown coloration, and cancer, etc., due to presence of a heavy element present in the cosmetics. In present work, I have studied the nanosecond laser interaction and elemental analysis of cosmetic agents using spectroscopic techniques. The cosmetic samples are taken from Hyderabad, Sindh, Pakistan. Introduction of LIPS. LIPS basically stands for Laser Induced Breakdown Spectroscopy. It is an analytical technique through which one can determine the elemental composition of any sample. Sample may be in the form of a solid, liquid, as well as a gaseous form. Overview of LIPS process. Basically, LIPS process consists of three separate regimes. One is known as a plasma generation, second is known as a light collection, and third one is known as a spectral analysis. During plasma generation, a highly powerful laser light interact with the target material after passing from focusing lens. This focusing lens basically focuses this laser light into a small portion or small area of the target material. So as a result, plasma is generated in the form of plume. So as the plasma recombine, this plasma emits radiations, and these radiations are collected by a spectrometer. This is a device which absorb radiations and converts these radiations into electrical signal. So finally we get a spectrum, and we will analyze this whole spectrum, and this spectrum tells us about the information of this target material. LIPS process can be classified into three separate operations. One is known as a laser material interaction, second is known as a laser plasma interaction, and third one is known as a plasma expansion. During laser material interaction, a highly powerful laser light interact with the target material. So as a result, plasma is generated on the surface of target material. So this plasma exists here in a nanosecond, while another laser light interact with this plasma. So this interaction is known as a laser plasma interaction. As a result, a high pressure is generated inside the plasma, and plasma expand in the form of balloon. So this procedure is known as a plasma expansion. So these are the names. Material ablation. Material ablation, it is a process of a removal of material from a surface by heating it with a laser beam. So this material removal depends on two properties. One is known as a laser property, second one is known as a plasma property. So laser property may be pulse width, wavelength of a laser, energy of laser, and sample property may be optical properties or thermodynamic properties. So what happens here, when a laser light interact with this target sample, so as a result plasma produced on the surface of this sample, and this is the result of a material ablation. So this plasma or material ablation depends on two properties. One is a laser property, second one is a sample properties. So creation of plasma on a cosmetic sample using LIPS technique. So this is the basically our target material, and here this is a sample holder. Here is our target material. This is a convex lens, and from this side our laser comes and interact with this target material after passing from this convex lens or focusing lens. So as a result, plasma is generated. So due to recombination, plasma emits radiations, and these radiations are collected by spectrometer through optical cable. From this side, our optical cables are present which absorb radiations. So advantages of LIPS. LIPS has many advantages, just like it offers rapid analysis, require no or very little sample preparation, require no contact with a sample, sensitive to all elements, analysis spot is very small, scalable in a sample size. It has a many applications, as LIPS has a many applications throughout the globe, just like material analysis, industrial analysis, environmental monitoring, biomedical analysis, military and safety application, etc. respectively. Sample preparation. So we have followed two steps to make a simple one. In first step, we take 10 gram of cosmetic, just like talcum powder, mixed with 3 gram of wax powder. So as a result, we put these both cosmetic and wax into mixing machine. So after that, this process, in next step, we take 10 gram of this mixed material and put into this electrohydraulic press for making hydraulic press for making our plates, that due to which we will analyze by hitting the laser on those plates. So finally, our plates are ready for data analysis. Samples. I have basically my cosmetic agent was basically talcum powder, and I have taken three different talcum powders. One is Enchanter, this is coded as a sample A, Kiriza, sample B, and Fair and Cute, sample C. Sample A belongs to Malaysia, sample B belongs to England, and sample C belongs to Pakistan. These are the most popular cosmetics or talcum powders used in Pakistan. Experimental setup. So our experimental setup consists of a NDOG laser, lens. This is lens is a basically focusing lens, simple holder, probe, and spectrometer, delay generator, and power supply. Finally, laptop or PC. So what happens when a laser light comes towards target material after passing from this lens, and this laser light interact with the target material? As a result, plasma is generated. So as a recombination of plasma, this plasma emits radiation in all direction. But we put our probe at the 90 degree of this plasma, and it's working. This basically absorb radiations and move towards spectrometer, and spectrometer converts these radiations into spectral lines. And this is the basically delay generator. And the working of delay generator is basically the delay or the time gap between plasma generation and the light collection. So the time gap between plasma generation and light collection uh, doing this work, delay generator. So again, this is the same picture which I've told you. So our probe is set. We have set our probe from this side, 90 degree to the plasma plume, and this is the perfect location of a probe. This probe basically absorb maximum radiations. That's why we place this probe at 90 degree of a plasma. Results and discussion. Emission spectrum of talcum powder plasma produced by 1064 nanometer laser. So this is our target material, and you can easily see there are multiple spots here. These spots basically laser shots, and we have taken multiple data and finally get average of all data. And the spectrum, whole spectrum consists from 300 nanometer to 780 nanometer. This whole spectrum, we will analyze this whole spectrum, and this whole spectrum gives the information about this target material. So this whole spectrum were further divided into portions for perfect identification of transition lines or emission lines. So in a figure A, which consists from 305 to 380, we have observed four emission lines, and these four emissions belongs to calcium neutral line, calcium ionic lines. In a figure B, it starts from 380 to 433. We have observed three magnesium lines and remaining calcium lines. In a figure C, it starts or is ranging from 440 to 489. Almost we observed all transition lines of belongs to calcium. In a figure D, it starts from 500 to 530. We have found silicon, magnesium. These are the triplet of magnesium, calcium, and calcium lines. In a figure E, it starts from 530 to 600. Most from in this portion, we have observed chromium, calcium, aluminum, calcium, and doublet of a sodium line. In a figure F, which is start from 608 to 618, we have observed triplet of a calcium line. In a figure G, its ranging is from 632 to 648. We have observed two silicon lines, one strontium line, and remaining calcium lines. While figure H, its ranging is from 648 to 672. We have observed three calcium lines and one H alpha line. This is basically hydrogen, neutral hydrogen lines. In the last figure I, it start from 710 to 710 to 735. We have observed three calcium lines. Number of emission lines of all samples. Basically, we have observed these emission lines or these elements in a sample A. We have observed 19 calcium line, while in a sample B, we have observed 42 calcium lines. In a figure C, we have observed 19 calcium lines and minor calcium lines of magnesium, silicon, chromium, and strontium, aluminum, sodium, hydrogen, and lithium. Temporal variation of intensity. Temporal variation is basically a variation of anything or intensity along with a delay time. Temporal basically a variation shows a variation with a delay or variation with time. So this is a basically 3D graph, and this 3D graph shows that the emission lines or the intensity of emission line continuously decreases as the delay increases or delay time increases in a microsecond. So let's suppose this is our target material and plasma plume is produced or generated normal to the target material. So we put our spectrometer or probe at this position. This position is basically core of plasma, and we changes only, we does not change this probe. That means we does not change distance, but we only change delay time. Delay time basically the time gap between light collection or plasma generation and light collection. So as you increase the delay between plasma generation and light collection, the intensity of transition line continuously decreases. This is due to recombination of plasma. Axial variation of intensities of transition lines. So axial means a variation of a transition line or variation of intensities along with the distance. So this equation shows that the intensity varies according to this equation, and the intensity does not varies only with a temporal variation, but intensity varies along with the axial distance or variation also. So again, let's suppose this is our target material and this is a plasma plume. So now this position, we does not change delay time, but we only changes a distance. As we increase distance normal to the target material, again intensity continuously decreases. The variation of intensity depends on this equation. So these are the names. H is a basically Planck's constant, C is the speed of light, lambda is the wavelength of transition line, G is the transition probability, A is the transition probability, and G is the statistical weight. Likewise, EJ is the upper energy. Temporal and axial variation of Stark shift of emission line. So there are 4 pictures, A, B, C, and D. These all pictures shows that there is a variation of a shift. There is a variation of transition line. This variation is known as a shift. So this shift occurs due to Stark shift. This is known as a Stark shift. This occurs due to the microelectric field produced inside the plasma, because we know that plasma is basically highly ionized gas or highly ionized charged particle. So there is an electric field, and that electric field is known as a microelectric field. Due to this, there is a transition occurs. So this emission line belongs to neutral lead 266.3131. So there is a shift. This black in transition line recorded at 1 microsecond, and this last one having a low intensity recorded at 6 microsecond. This means we change the delay time, and there is a shift. That shift is known as a Stark shift, and remaining pictures are again behave like a same. Plasma parameters. There are the number 1 is known as the electron temperature.
Excuse me, sir, I
Electron
want to ask a question.
Okay.
I want to ask a question from previous slide.
Okay, this one.
Yes, sir. सर इस ग्राफ में जो वेरिएशन है वो किस के दरमियान आ रही है? ये डिफरेंट कलर के ग्राफ्स हैं, तो ये किस मतलब वेरिएशन किन पैरामीटर्स में आ रही है?
अच्छा, ये जो वेरिएशन है, हमें जो फर्स्ट ब्लैक वाला जो लाइन है दैट इज रिकॉर्डेड एट 1 माइक्रोसेकंड. ये हमने 1 माइक्रोसेकंड में रिकॉर्ड किया, और जैसे ही एज द डिले इंक्रीजेस द इंटेंसिटी ऑफ ट्रांजिशन लाइन कंटिन्यूअसली डिक्रीजेस. ओके, this shows that just not intensity decrease, but there is a variation of shift
in
that shift
time.
Okay, in delay time.
Okay sir, okay, thank you.
So electron temperature is a measure of average thermal kinetic energy per particle in a plasma. Electron temperature is an important parameter to describe the ionization and excitation process takes place in a plasma. Intensity ratio method and Boltzmann plot method are used to determine electron temperature. So this is the formula of electron temperature using intensity ratio method, and this is the formula for calculating temperature or electron temperature using Boltzmann plot method. So we have used this method
We
to
have another
calculate
question,
plasma temperature.
Dr. Said. We have another question.
Okay.
I think one of the attendees have raised the hand. So
Okay, which one? Kindly.
you may open the mic and speak. Oh, I think maybe we can let the questions till the end.
Okay. So can I move on?
Okay, because there was some raising hands. If it is urgent question, you can write in the chat. I will to answer if it's regarding some slides, or we can make discussions at the end of presentation. Sorry for the interruption, Dr. Said. You may continue.
Okay. So I have used this equation, Boltzmann plot method, for calculating electron temperature. So I have used these transition lines to calculate electron temperature. These transition lines basically belongs to calcium neutral lines. So this graph is known as a Boltzmann plot or Boltzmann plot graph. And from this position, we have found first we found slope. Slope is equal to y2 minus y1, x2 minus x1. So after finding slope, we would put slope value here and find temperature. That temperature is known as the plasma temperature or electron temperature, where K represents Boltzmann constant. So the temporal variation of electron temperature. So this graph shows the temporal variation of electron temperature with a delay time. So first one belongs to simple C, central one belongs to simple P, and last one belongs to simple A. So these variations shows that as the delay time increases, the temperature of plasma continuously decreases. This is again due to thermalization or recombination of plasma. So plasma, as a plasma recombine, the temperature of plasma or the average kinetic energy of molecule continuously decreases, due to which the temperature variation shows that due to which the temperature variation also decreases, and this shows exponential decreasing trend. For sample A, we have found 11,000 to 3,050 Kelvin temperature. For sample B, we have found 12,400 to 4,300 Kelvin. And for sample C, we have found electron temperature from 13,700 to 4,910 Kelvin. Next one is the electron number density. Electron number density is the number density of electrons in a plasma. Electron number density is also an important parameter to describe the state of plasma. So Stark-Broadband line profile method is used to determine the electron temperature. So this is a formula of Stark-Broadening line profile method. The delta half lambda is basically full width of maximum, and omega is basically an impact parameter which we can check from literature. Ne is the electron number density, and this is the power factor. We can multiply this. So this is another formula of electron temperature. So this is a special formula. So this formula you can use when you have a hydrogen line. So if you have a hydrogen line, you must use this formula for calculating electron number density, because by using hydrogen line, you can minimize your errors. Temporal variation of number density. So this graph shows for sample A, for sample B, and for sample C, number density continuously decreases as the delay increases. But number density,
Excuse me, sir.
number density, yes.
Sir, what is impact parameter?
So can you
ओमेगा
ask
आपने
these
कहा
questions from us?
आपने कहा ओमेगा इम्पैक्ट पैरामीटर है इम्पैक्ट पैरामीटर क्या होता है
इम्पैक्ट पैरामीटर कुछ वैल्यूज कैलकुलेटेड होते हैं जो कि लिटरेचर में गिवन होते हैं, ठीक है, तो उनको वहां से डिटेक्ट किया जाता है.
ओके सर And sir, what is the
for
purpose
sample
of
A,
finding plasma temperature and electron number density?
so one request from you, वो ये है कि आप अगर क्वेश्चन लास्ट में करें तो बेहतर रहेगा.
Okay, sir.
ठीक है, thank you very much. For sample A, electron number density varies from 9.29 to 4.49 into 10 power 16 centimeter power minus 3. For sample B, electron temperature varies from 7.71 to 3.62 into 10 power 16. And for sample C, this electron density varies from 6.54 to 2.19 into 10 power 16 centimeter power minus 3. Again, number third is the plasma frequency. The oscillating frequency of plasma species is known as a plasma frequency. The laser meter is also depends upon the reflectivity of a target surface. The laser pulse absorption or reflection from the target sample depends on a plasma frequency. So this is our formula for calculating plasma frequency. So omega p is equal to 9 into 10 power 3 radical Ne. So this shows plasma frequency depends on a electron number density. So as our electron number density decreases, that means the plasma frequency also decreases. So this is the decreasing trend, or this is the graph of plasma frequency versus delay time of a talcum powder samples. For sample A, it varies from 5.51 to 3.83 into 10 power 10 hertz. For sample B, it varies from 5.02 into 10 power 10 to 3.43 into 10 power 10 hertz. For sample C, it varies from 4.62 to 2.68 into 10 power 10 hertz. So again, this shows the decreasing trend. So I have already told you that there is a recombination occurs in a plasma. So as a plasma recombine, the energy of plasma continuously decreases. So as energy decreases, the oscillation of these particles continuously decreases. As the oscillation decreases, that means the frequency decreases. So this trend occurs due to that. Next one is the IB coefficient, that means inverse Bremsstrahlung coefficient. The inverse Bremsstrahlung is a process in which an electron absorbs a photon while colliding with another electron or ion. Electron temperature and electron number density are the most popular parameters that can be utilized or explore the existence of plasma configuration. The inverse Bremsstrahlung coefficient is an important parameter of production of a plasma. This is the one of the main parameter for the production of plasma or plasma generation. So this is the formula for calculating inverse Bremsstrahlung coefficient. Here alpha IIP basically inverse Bremsstrahlung coefficient, lambda is basically laser wavelength, N is the electron number density, and T is the electron temperature. So this is the variation of a inverse Bremsstrahlung coefficient with a delay time. For sample A, this varies as 1.36 into 10 power minus 3 to 6.02 into 10 power minus 4 centimeter inverse. For sample B, it varies as 8.81 to 2.28 into 10 power minus 4 centimeter inverse. For sample C, it varies from 6.04 to 1.44 into 10 power minus 4 centimeter inverse. Next one is the calibration free ellipse. So calibration free ellipse is the technique which is used to determine the concentration of element present in any sample. So for atomic species, we use this formula FCZ. F is a normalization factor, CZ basically concentration is equal to IK. I is the integrated intensity, UZ, this is a basically partition function, A is a transition probability, G is a statistical weight, EK is upper energy, K is a Boltzmann constant, and T is a temperature. And this equation is used for ionic species. So let's suppose you have both calcium lines, calcium 1 that means calcium neutral, and one is the calcium 2 that means calcium ion. So for neutral you use this equation, for ionic line you use this equation, and finally you just add both concentration for finding total concentration of element present on that sample. The concentration of element present in a talcum powder sample. So these are the values, and we have used two techniques. One is the calibration free ellipse, and second one is the AAS. AAS basically atomic absorption spectroscopy, and this is again used to calculate the concentration of elements present in any sample. So for calibration, due to calibration free ellipse, we have found maximum concentration of all samples and a minor concentration of magnesium. We have now found chromium in sample A, but we have found chromium for sample B and not for sample C. Lead, zero concentration using calibration free method. But we again, for verification of these results, we used AAS technique, and this shows that again calcium has a maximum concentration. That means this result supports the calibration free lips. So this shows that during calibration free or AAS, we have found maximum concentration of calcium in a talcum powder sample. So this is the ETX, energy dispersive X-ray, and this result shows that there is a high weight percentage of calcium in our sample. Error budgets. There is also fluctuation in the reproducibility of the data due to the following reason: fluctuation in a laser energy measurement, fluctuation in a length to sample distance, roughness of a sample, geometrical position of a sample surface with respect to laser. Conclusion remarks. We have see that LIPS is a very useful technique for elemental analysis of a material. And for sample A, we have found these emission lines: calcium, sodium, hydrogen, magnesium, silicon, aluminum, lithium. For sample B, we have found calcium, sodium, hydrogen, magnesium, silicon, chromium, strontium, aluminum. While for sample C, we have found calcium, sodium, hydrogen, magnesium, silicon, and aluminum. Our results shows the intensity variation of emission lines decreases with temporal variations. Not only temporal variation, but axial variation also. Stark shift occurs in transition lines due to microelectric field present in a plasma. We have found the maximum concentration of calcium in all talcum powder samples using calibration free lips, AAS, and EDX techniques. Calcium on the skin not only protect the skin from UV radiation, but also contribute to regulate the dead skin cells lysis and new skin cell regeneration. So there is a benefit of calcium in our skin. So this is a LIPS technique, LIPS setup in Cairo University, Islamabad. We have recorded our data from this lab. This is a main source that is known as Endiog laser. This is a power supply, and this is a delay generator, and this is a sample holder, and this is basically our probe, and this is our spectrometer, and this is a reflecting glass. So my talk, elemental analysis of talcum powder. So this is our work is published on optic, is a highly rankable journal. Its impact factor is 2.449, and our topic is elemental analysis of talcum powder using spectroscopic techniques. This is recently published 2022. List of publications. My one paper is just accepted yesterday and will soon available on online, and these are the publications. And this is, thank you for your valuable question. House is open. Thank you.
Assalamu alaikum, sir. Sir, what is the purpose behind finding the plasma parameters like electron number, density, and plasma temperature? Why do we find
पैरामीटर फाइंड करने का फायदा जो है हम इसलिए ये फाइंड करते हैं कि हम बेसिकली वी वांट चेक द बिहेवियर ऑफ प्लाज्मा. So if you want to check the behavior of plasma, so that's why you need to find out these parameters.
Sorry sir, I couldn't understand. Please repeat.
देखिए प्लाज्मा पैरामीटर जो है वो इसलिए हम फाइंड करते हैं कि प्लाज्मा जो हमारे पास बन रहा है वो किस तरीके से रिकम्बाइन हो रहा है, रिकम्बाइन एक्सपोनेंशियली हो रहा है या स्लो स्लो रिकम्बाइन हो रहा है. तो इस वेरिएशन को देखने के लिए हम इन पैरामीटर्स को फाइंड आउट करते हैं.
And sir, applications of laser induced plasma. Sir, applications of laser induced plasma.
जी, एप्लीकेशंस जो लेजर इंड्यूस्ड ब्रेकडाउन स्पेक्ट्रोस्कोपी है वो हर जगह पे हैं, जैसे कि मिलिट्री और सेफ्टी एप्लीकेशन अगर देखें.
सर लेजर इंड्यूस्ड प्लाज्मा
करते हैं.
जो प्लाज्मा है वहां से बनता है, जो उसको हम कहाँ यूज कर सकते हैं? जो लेजर इंड्यूस
उसको
प्लाज्मा
हम
जिस तरह
यूज नहीं कर
जनरेट हुआ है, जिसके हमने पैरामीटर्स फाइंड किए हमने, क्या उसको हम यूज कर सकते हैं?
No, we cannot use this parameter plasma because its lifetime is very short.
ओके ओके ओके।
Okay, thank you. Farkhan Danur?
Is there
Yes,
any
sir.
question?
सर माय क्वेश्चन इज दैट कि जैसे आपने कहा है कि आपने यहाँ पे वैक्स पाउडर को भी यूज़ किया है विद कॉस्मेटिक पाउडर, तो इज इट नेसेसरी?
Yes, this is necessary for creating bonding of between cosmetic particles.
Okay, sir. Sir,
Without
my
this,
second
we
question.
cannot. Hmm,
My second question is that can the delay time affect the results? If yes, then how? Delay time, as you
what
have
do you mean?
mentioned, how
So
can it
delay
affect
time
the
affects
results?
the results. So let's suppose plasma is formed. Okay,
Yes.
plasma is the high temperature, and the environment surrounding the plasma is very low temperature. As there is a law of physics, temperature always from higher to lower. So as the delay increases, the temperature or the particles present in the plasma continuously, their energy continuously decreases. That means the temperature decreases. So as the delay increases, this variation continuously increases. And this behavior is known as the temporal variation. Okay?
Okay, sir. Thank you, sir. My last question is, as you have mentioned that you were talking about talcum powder, and you have said that it is affected for our skin, but in the end, you were saying that calcium is good for your skin.
Okay.
Uh, can you say if we can say that calcium is in high pop in is in uh, I mean, uh, uh, if calcium is greater in, then it is good for health. I mean, it is good for skin or not. If
Yes. The my
if the
results only
if the value
belongs
of
to
calcium, yes, sir.
my results only belongs to those samples which I
I mean, what the
used
objectives of
this
your
process.
what the objectives of your work? What are the
Hello.
objectives of your work?
My objective was to find out heavy elements and their concentration. So we have found there's no any heavy elements, and the concentration of calcium is very high, and this is beneficial for our skin. So this protect UV radiations from our skin. So these results are only belong to those samples which I have used in this process.
Okay, sir. Thank you, sir.
Okay, next one, Ghanshyam Das.
Thank you, Dr. Saifullah, and we thank
From
all the
Israel.
attendees. We will send an evaluation, a link for evaluation on the Telegram group. Please evaluate the seminar today, and in the evaluation form you will find a question to write your full name so you can receive your certificate of attendance. Thank you again, and now Dr. Ayman Al-Sharqawi will give thanking talk to Dr. Said.
Thank you very much, Dr. Saiful Din. Is very informative lectures, and thank you for everybody and for all attendance. Thank you.
Now the session will end. Thank you again.